Hey guys, welcome to our lovely video here on solutions to systems of equations using matrices. Um, Systems of equations are things that you've probably dealt with in the past, and the first couple examples are gonna be using some of the old methods to solve them, to remind you how painful it is. And then we're gonna make things a lot nicer and simpler for you. So let's start with a lovely little example or a little kind of refresher. So a system of equations in two variables, or it could be three or more, right? We could have, seven variables or anything like that. But in the past, we've done them using two variables. And you can see that like in this example one here, we've got our two equations, 2x plus 3y equals -1, and x minus 2y equals 3. So to solve this system means to find an ordered pair, a value for x and a value for y, that satisfies or makes both equations true at the same time. Okay, so we're trying to find an x and a y value that when we substitute into the first equation, it gives us a true statement. We substitute in the second equation, also gives us a true statement. So when I mean true statements, we're talking 5 equals 5. False statement would be things like 0 equals 7. Okay, so up until now, we've had three methods to solve these. We could do them graphically. By graphing. We could substitute. Or use substitution. And lastly, with elimination. Okay, so these are the three methods that we use for solving systems equations. The way we do it graphically, right? If you imagine having a graph, and then we've got equation 1, equation 2, then this point here would be our solution. This xy is the solution to that equation. Okay, so now let's talk about using substitution to solve this. To do substitution, what we need to do is take one of our two equations and solve it for one of the variables. Since the first equation, 2x plus 3y equals -1, both variables have a coefficient, but in the next equation, we notice the x has no coefficient, or it has a coefficient of 1. So that's going to be easier to solve for x. So we're going to start with that. So we have x minus 2y equals 3. Add 2y to both sides. X equals 3 plus 2y. So now we have this value for x, and we can substitute that into our other equation. And so when I do that, I get 2 times, so instead of x, we have 3 plus 2y plus 3y equals -1. Now we distribute, giving us 6 plus 4y plus 3y equals -1. Combine like terms, 6 plus 7y, -1, subtract 6, and 7y equals -7, divide by 7. We see that y equals -1. Now, we know what y equals, so what we can actually do is we can take this value here and substitute it into here, and so we get that x equals 3 plus 2 times -1, so x equals 3 minus 2, which is 1. So our solution to this system is the order pair 1, -1. Well, that's it. So that's not too bad, right? Okay. But what about this next one? Elimination method. So the elimination method, notice this is the same systems of equation, so we should be getting the same resulting solution. Now, to use the elimination method, what we wanted to do is we want to make coefficients of the same variable in the two equations equal but opposite. So we're looking to have, say, the coefficients of x be 5 and -5. And what we're going to then do is we're going to add the two equations together. And what that's going to give us is it's going to give us some canceling of variables. Okay. Now, first of all, the reason we can add these together, if you think back to exponential functions, and we found exponential functions that went through 2 points where we didn't know the y-intercept, right? We create the two equations from the 2 points, and we divided one equation by the other, right? Because those equations are equal, so what we're really doing is dividing by the same thing on both sides. Here, when we're adding these two equations together, we're really adding the same thing on both sides. We're just choosing it to look two different ways. So like, if you will here, x minus 2y is equal to 3. So if I add 3 to -1 and I add x minus 2y to 2x plus 3y, I'm really adding the same thing on both sides. It just looks different, okay? So the first step here is to get equal but opposite coefficients. And there's a couple of ways you could do it. Some people will say, oh, well, that x has a coefficient of 1, so I can make it whatever I want by multiplying that 1 really easily. Others will say, well, the y's have a positive 3 and a negative 2. So they're already opposite, so let's just make them equal from here. And so what we mean by that is, so we need to find a least common multiple, or just really a common multiple if you want to make it simple, of both 3 and 2. And in this case, it's 6. And so what we're going to do is we're going to take the equation 2x plus 3y equals -1. Okay, and on each side, we are going to multiply by 2. Okay, and when I do that, I get 4x plus 6y -2. And now with the equation x minus 2y equals 3, I'm going to multiply both sides by 3. And that, when I distribute, will give me 3x minus 6y equals 9. Okay, so now notice my y's have equal but opposite coefficients. So on this one here, we have a positive 6, and over here we have a negative 6. So now I want to add these together. And so kind of the shorthand way of writing that out is we do something like 4x plus 6y equals -2 plus 3x minus 6y equals 9. It's kind of like an old school long division here, or long addition. And so what results, so the equals just kind of rolls down. So -2 plus 9 gives us 7. 6y plus -6y gives me 0y. And if we have 0y, we don't have to write that down, right? And then 4x plus 3x gives me 7x. Divide both sides by 7, x equals 1. Now that we know x equals 1, we can go back and plug that into one of our original equations. It really doesn't matter which one. And we can then solve it. So let's go 2 times 1 plus 3y equals -1. So 2 plus 3y is -1. Subtract 2. 3y equals -3. Divide by 3. And we get y equals -1. Okay, so our solution is 1, -1, which is the same that we got last time. So that's awesome. That's perfect. That's what we're looking for. So we have now done this in two different ways, both by substituting and by elimination. But what happens if I have a system of equations with more than two unknowns? What if my system of equations were something like, say, x plus y plus z equals 5, 2x minus 3y plus 2z equals 17, and say -x minus 4y plus 2z equals 10. I don't want to graph these because those are three-dimensional spaces. So what these represent in 3 dimensions. So if you imagine the world we live in is a 3-dimensional world. And essentially what these are is we have a left amount, a right amount, and an up-down amount. So if you look down at the table you're sitting at, or whatever flat surface you're sitting near, if it's your bed or a table or couch or whatever, imagine that is like the x and y axis. And then the z-axis is coming straight up and down out of the table and below the table. And so kind of if your x value is 5, if you will, kind of imagine a coordinate system on your table. X is 5, moves to the right 5 from the 0, 0, 0 spot. Y is 2, it goes up 2. If z is 5, then lift your finger 5 points up off of the table, essentially, and that's that point. However, these equations represent what are called three-dimensional planes. So if you imagine it's a flat surface that extends infinitely far in every direction. So if you take two dimensions and think of a line, right, that goes infinitely far both ends, a three-dimensional version of that is a plane, and it then takes that line in one dimension and also extends it infinitely far out in the other direction. I don't want to have to try and graph these and find this point. That's not an easy thing to do. Our calculators can't handle it. Our calculators can't really handle graphing three dimensions. Some computers can. Some computers can do it better than others. Now, if I wanted to use, say, substitution, I would not just have to solve for an x, but I'd have to solve for at least two of these variables. So I'd have to get an x equals something and a y equals something. And that would be something like x equals, so in this first one, we'd get like x equals 5 minus z minus y. And then we would have to do that again for another variable and then plug both of those into the other equation. And it just gets really messy really quick. And so what we can do instead is using matrices to help us. So let's talk about what a matrix is, okay? Before we talk about how we can use them. So very simply, a matrix is a rectangular array of elements. Now we say elements instead of numbers, and the reason for that is because matrices don't have to be numbers. They can have letters, they can have variables, they can have all sorts of things. And so we always say elements just to keep us more general. And then the dimensions or the size of the matrix is always denoted by the number of rows by the number of columns. Okay. So we think the number of rows, so rows go left and right, columns go up and down. A nice way to think of it is if you're looking at from a stage, looking out onto the audience, the rows are going across. Okay. Or if you look at a building and it's got these columns, those are things holding up the roof, right? So columns, rows. Okay. So to give the dimensions of each matrix. So this is a very simple one. There are two rows, 1, 2, and 1, 2 columns. So this is a 2 by 2 matrix. Our next one also has 2 rows, but it has 1, 2, 3 columns. So this is a 2 by 3 matrix. This one here, we have a 1, 2, 3, 4 rows and 1 column. So this is a 4 by 1 matrix. And this next one has 1 row and a 1, 2, 3, 4, 5 columns. So let's say 1 by 5. This one has 1 row, 1 column. So let's say 1 by 1 matrix. So being able to identify the size of a matrix is an important ability, especially if you're doing certain matrix operations. We aren't going to do those a whole lot, but I guarantee you I'm going to ask you to identify the dimensions of a matrix. So know how to do this. So we typically, in general, if a matrix has m rows and n columns, we say it is an m by n matrix. Right? That's our kind of generic-y annotation of matrix dimensions. Now, this next definition is what we're going to be working with to solve these systems of equations. Okay. A system of equations can be put into a matrix by writing it as an augmented matrix. Augmented matrix. This is sometimes called a coefficient matrix. Okay. And so it's a really simple way to write a set of matrices. And so we're going to look at this first tier example here. This is the system. Notice this is the system we've been dealing with in examples 1 and 2. We already know our solution to this. We'll find it using matrices here in just a minute. But right now, we just want to practice putting this into augmented form. And so the way it works, okay, so our matrix, notice the way these are written. These have these square brackets. Okay, so since this is a system with 2 equations and 2 unknowns, okay, our augmented matrix, I'm going to draw this really big. It doesn't really need to be this big. Okay, each row represents a matrix. So I'll kind of like to kind of help us start with this. I'll say this is like equation 1, equation 2. Then each column represents the coefficients of a variable. And then the final column is the equation's result. And so the way I kind of help annotate this to kind of help us think about it is like this. Okay, so for this system, this is the way I kind of annotate the outside of the matrix. This is absolutely not something you're going to do every time. This is something that we're doing this time just to help us kind of visualize and see what's going on. As you get comfortable with this, you will not do this. Notice there's nothing on the outside of these matrices except for the tick marks I made when counting. And so that's just kind of how we are going about that. So what we want to do is we want to say, okay, in equation 1, what is the coefficient of x? So we look at equation 1. It doesn't matter which one's equation 1, just pick one and stay with that. Don't change halfway through the problem. The coefficient of x is 2. So we have a 2 right here. In equation 1, what is the coefficient of y? 3. And in equation 1, what is the result? It's -1. Okay. Now, in equation 2, what is the coefficient of x? There isn't one, but if there's no coefficient there, but we still have the variable there, we know it's always a 1, right? Because 1 times x is just x. In equation 2, what's the coefficient of y? It's -2. And in equation 2, what is the result? It's 3. And so this is an augmented matrix. And now sometimes what you may see in an augmented matrix or coefficient matrix is you may see something where it has like a bar like this. And what that bar is doing is it's separating kind of our coefficients of x and y and the results. And that's all that's there for. It has no mathematical purposes. It is purely a visual separation. You'll never type something like that into a calculator. You'll never see that on a calculator. If you advance further in mathematics to deal with more matrices, you will not see that in a practical sense there outside of just kind of helping you to visualize things and work things out that way. I typically don't put it, but feel free to put it on there if you want. Some of the questions in the homework may have it or may not. Same for the test, but for the most part, I try not to use that just because it's not necessary. Notice here, what are the dimensions of this matrix? The dimensions of this matrix are 2 by 3 because we have 2 rows and 3 columns. Notice that is the number of rows is equal to the number of equations. And the number of columns is equal to the number of variables plus 1, right? That plus 1 gives us that result column. And so we can always look at a system of equation and we'll know exactly how many rows and columns it's going to have based on what's going on. So like this next one, we can look at this and see I have 3 equations. So the dimensions of my matrix are going to be 3 by, and I have variables x, y, and z. So I have 3 variables plus 1 is 4. So this matrix, this augmented matrix, will be a 3 by 4 matrix. That's pretty cool. Okay. Now, there's a couple of things that are important when we're looking at equations and going into our matrix. So this first one here, we had our x's were right on top of each other. So I'll use my highlighter here. Our x's are on top of each other. Our y's are on top of each other. Our results are on top of each other. But over here, notice that I have an x here, here, and then here. So those aren't on top of each other. I have a y here, here, and over here. I have a z here, and I have no z here. And then my results are on top, so that's good. Okay, but what do I do to get this in automated form? I could absolutely leave it like this and just be careful in my kind of identifying of the coefficients, right? By kind of very carefully going, okay, in equation 1, the coefficient of x is equation 1, the coefficient of y, go through that way. Another thing I could do is I could reorder this system so that my coefficient or my variables all occur in the same order. And so the first equation I'm going to leave, that's going to be kind of my set one. It's also kind of the order we want, x, y, then z. So it gives me 2x minus 5y plus 6z equals -3. Notice the way I did my z, I put a little line through my z's because if I don't, my z's and 2's end up looking very similar, and it can be very confusing. So my next equation, I want to rearrange things so that it goes, my variables go x, then y, then z. And so I need to move this plus 3x to the front. And then I have a positive 7y, so we can plus 7y. And I have a negative 3z, so minus 3z. And that equals 8. Our next one, I have an x plus 7y. And then I have, there's no z's, so I'm just going to leave that blank. That equals 5. Okay. Now, you may be wondering why I left the space here, partly because so I can line up my equal signs, but it also helps us when we're creating our matrix. So let's create our matrix. Okay. Again, equation 1, equation 2, and this time equation 3. We have our x's, our y's, our z's, our result. Now, these things right here, if you're comfortable, do not write them. That's fine. As we get further on into this lesson, this is probably going to be the last time I'm going to write those out. From here on out, I'm just going to write my equations and go from it. So in equation 1, the coefficient of x is 2. In equation 1, the coefficient of y is -5. In equation 1, the coefficient of z is 6. And in equation 1, the result is -3. We have equation 1 done. We have row 1 done. Let's move on to row 2. In equation 2, the coefficient of x is 3. Coefficient of y is 7. Coefficient of z is -3. And the result is 8. Now, if we wouldn't have reordered these like we did right here, it's very, very common that if I were to give you a problem like this, that you would have put this row as 7, -3, 3, 8. Because you would have just said, okay, this first, then this, then this, then this. But we have to remember that they are specifically going with a certain variable, so we have to keep those in line. Now, equation 3. What's the coefficient of x? Well, again, we have an x by itself, so that means its coefficient is a 1. Y is easy, that's 7. But what's the coefficient of z? We don't have a z. There's no z there. So think about this. What do you multiply by z so that it goes away? Right? If I multiply by 1, the coefficient goes away, but I still have the variable. I don't have the variable here. So that means I have to multiply by 0. So that means the coefficient of z is 0. And then our result is 5. All right. So that's that problem. Now let's talk about how do we go from a matrix back to a system of equations. Okay, it's actually really easy if you just kind of remember the way we created our matrix from our system of equations, right? So if you will, this would be equation 1, equation 2, equation 3. Here's our x, y, z, and the result. So that means equation 1 is going to be 1x. Now you could write a 1 there if you want, but we're going to go ahead and assume some mathematical sophistication that you guys all have, and we know 1x is just x. We're just going to leave it like that. If you're more comfortable writing the number and then that and then simplifying later, that's perfectly fine. But we're going to try and strive for a little bit more sophistication since we're almost to the end of this term. So we have a 1x, we have a positive 2y, so plus 2y, a positive 3z, so plus 3z, and that result is -4. Our next one, our equation 2, we have a 0x. So again, if you feel comfortable doing this, if this is what makes you comfortable, you could write 0x and then simplify later. But I know if I multiply anything by 0, it goes away. So I don't want to write 0x, I just want to write nothing. I just want to leave it blank. And then I have a plus 1y, so that's just a y. And then my coefficient of z is -6, so I have minus 6z, and that result is 7. And in our last row, we have a 0. So our last equation, we have 0x and 0y. So those are both just gone. And then we have a 1z. So what we have is z equals, and the result is 8. Okay. That's terrible. Okay. Now, we have converted this matrix into a system of equations. Now, notice it says then to solve. And this system is actually really easy for us to solve because of the way it's set up. If you notice, if we look at this portion of this matrix, it looks very nice, right? We've got ones on that diagonal, and then we've got zeros below them. And now this diagonal here is referred to, I'll do it in a different color, as the main diagonal. Okay. And so what that means, the main diagonal, is it's the first row, first column, second row, second column, third row, third column, right? Because we also have, we have diagonals, here, 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 here. Like we have lots of different diagonals. But this is the main diagonal because it's that first row, first column, second row, second column, third row, third column. Okay. That's important. Main diagonal. It's a term that we're going to use here in just a minute. So we have this cool form where we have ones on the main diagonal and zeros below those ones. And that gives us this kind of cascading equation, system of equations, where we have this only has z, this has y and z, and this has x, y, and z. So what I can do is I can use a method called back substitution. Back substitution is where we have the value for one equation, and when we plug that back into the equation before it, solve that one, then plug it back in before that. So I know already z equals 8. So I can use that to help me, and I get that y minus 6 times 8 equals 7. Well, 6 times 8 is 48, so we get y minus 48 equals 7. Add 48 to both sides. We get y equals 55. I normally do that below, but I'm kind of running out of room, so I didn't want to jump it. So now the next equation we have, notice x here has got a coefficient of 1, so that's really nice. We get x plus 2 times y is 55. Plus 3 times z is 8. And that equals -4. So if we simplify these, we end up with x plus 110 plus 24 equals -4. So we get x plus 134 equals -4. Subtract 134. We get x equals -138. So that means our solution here, since this is 3 variables, x, y, and z, it's not an ordered pair. An ordered pair is an x, y. This is an ordered triple. And so our solution is -138, 55, 8. And there we have it. So now let's look at row echelon form. Row echelon form is a very nice form of a matrix that helps us to solve equations doing back substitution. So row echelon form, which is also referred to as REF, okay, is when we have ones on the main diagonal of an augmented matrix. And zeros below the ones. Okay, so that is exactly what we had up here. So this is in row echelon form. We have ones along that main diagonal and zeros below. Okay, so solve this system using matrices. We've already converted this into a matrix, so let's just do that again real quick. So we get 2, 3, -1, 1, -2, 3. Now, to enter this into our calculator, okay, that is how we are going to do this. So, to enter into calculator, watch calculator, video. So this is going to be a second video that's following this that goes through entering a matrix into your calculator to solve systems of equations. I'll go through both doing row echelon form and also the next form that we're going to talk about here in just a minute. So to do this, I'm just going to write the buttons here. So we go second, and then you're going to hit the button that says x to the -1. So that's what the button looks like, and above it, it says matrix. Okay. And this is going to take you to a screen that has names, math, edit. Okay. If you have already created matrices at some point in time, or someone else did it on your calculator, you're going to have some things listed under names. You'll see, or you should always have A, B, C, D, E, F, G, and then so forth. But next to that, you should see some numbers if you have some created. If you don't have numbers there, that just means no one's created a matrix. Unfortunately, to delete matrices out of your calculator is a bit more complicated than just like highlighting and hitting delete or clear. So don't worry about that. Just overwrite or erase or just kind of rewrite the numbers every time. Okay. So what we're going to do is we're going to go to edit and then choose your matrix. Okay. So edit, and then let's just choose option 1, which is matrix A. Okay. From here, you have to enter the dimensions. Okay. So the first thing when you hit, so you go second in the matrix, go over to edit, choose option 1 for matrix A. When you do that, it should kick you into a screen where it says at the top, it says matrix A, and then you should have a flashing, whoa, not a tube, flashing cursor. Stop creating tables. Okay, you know what? Instead of doing those lines, I'm just going to do this. Flashing cursor. Okay, and then there should be like an X and then a blank spot. Just type in the dimensions. So this matrix is a 2 by 3. So then you should type in here a 2 and then hit enter, and then 3 and enter. And now what you should see on your screen, it should look like this. And you can type in numbers into their spaces. And those numbers you want to type in are our augmented matrix. So 2, 3, -1, 1, -2, 3. So 2, 3, -1, 1, -2, 3. Okay, so that's it. Now, second, wait. And then, second matrix. And then we're going to go to math, and scroll down to option A, REF. I'm running out of room here, but it's all right. So once you've done that, okay. On your screen, it should say REF parenthesis. Now here's where we need to put the name of the matrix. So here is where you're going to go to matrix name, choose one. Okay. And so once you do that, your screen should now say REF parenthesis bracket A bracket A. Just hit enter. And what that's going to give you is it's going to give you your row echelon form 1, 1.5, negative 0.5, 0, 1, negative 1. And that is our row echelon form. Now that's great because then you can use that to back substitute and go through and solve. But I want to do better than that. Okay. Better than that is reduced row echelon form. Okay. Reduced row echelon form, or RREF, is just row echelon form, but with zeros above the ones as well. In other words, it would look something like 1, 0, 0, 0, 1, 0, 0, 0, 1, 3, 4, 5, like this. Okay, so this is a reduced row echelon form matrix. And that's how we're going to solve these systems of equations, is using reduced row echelon form. So let's look at example 8. We're going to solve this system using matrices, okay? And the only difference, so to get reduced row echelon form, the only difference, okay, is so in the calculator, you're going to choose math, then it's option B, RREF. Okay, so the first thing we have to do always is take our system of equations and convert it into an augmented matrix. This one's really nice. All of our coefficients pretty much are ones or negative ones. We have one of them that has a 2. So our first equation, x has a 1, y has a 1, z has a 1, and that equals 1. Our second equation, x is negative 1, y is 1, z is 1, and it gives us 5. Our last equation, x is 0, y is 1, z is 2, and we also get 5. So now we're just going to go to matrix, and we are going to go to edit, and we're going to choose option number 1 again, because remember, we don't want to delete these. Deleting is not an easy process. We're just going to rewrite. So when we go to matrix, edit, choose option 1, again, it's going to put that cursor in that first spot of the dimensions. We need to change our dimensions because we have a different dimensioned matrix in this problem. So we're going to change it to a 3 by 4. And then we just type these in, 1, 1, 1, 1. And so if you notice, if you're following along in your calculator, if you're not just waiting for that video, which is fine either way, as you're hitting the numbers and then hitting enter, it's moving you along the row. And so it goes from essentially the calculator starts here, it goes to here, to here, to here, and then it jumps back, then jumps to there, there, and there, and so forth. Okay. And so you can kind of go through, as long as you're not going too fast for yourself, you can pretty quickly get these matrices typed in. Okay. And so what you're going to do then is you're going to go through and use your calculator to put this into reduced row echelon form. Again, this is something that we're going to show in that second video. So if you're getting antsy on how to do it, pause this video, go watch that other video, and it'll kind of go through the calculator steps, and then come back here. Okay. So when we put this into reduced row echelon form, we are given this. So now that's great, but now how does that tell me what a solution is? Well, let's convert this back into a system of equations. And so to convert this back into a system of equations, right, we just go through equation 1, equation 2, equation 3, coefficients x, coefficients y, coefficients z, result, right? So in equation 1, the coefficient of x is 1. So we get x. Coefficient of both y and z are 0, which means they're not there. And the result is -2. So we get x equals -2. That's nice. In the second equation, the x has a 0, so it's not there. Y has a 1, so that's just 1y. The z is a 0, so that's not there, and that equals 1. In the final one, x is 0, y is 0, so those are both not there, and z is 1. That equals 2. Hey, x equals -2, y equals 1, z equals 2. So our solution here is the ordered triple, -2, 1, 2. Awesome. Let's solve these. Now, when I say let's solve these, I mean you are going to use your calculator and solve them. Okay? So, pause this video, try and do it. Now, if you get something weird and wonky, write down the reduced row echelon form and see what happens. And then play the video back and we'll get together and do it. All right. Pause the video, try to do it yourself. If you don't know how to do the calculator thing yet, go watch the calculator video, come back and solve these problems. Okay, this is on you. Ready? Go. Did you go? All right, well, not, you must be back then. All right, welcome back. Hopefully you guys are understanding how to create these matrices in your calculator and put them into reduced row echelon form. Now, this first one's really nice. Okay, I'm going to skip some stuff, namely the calculator button, pushy stuff. We're going to write the augmented matrix, then the reduced row echelon form, and then our solution. So this first one, our augmented matrix, that's terrible, bracket, is 2, 1, 2, 10, 1, 0, 2, 5, 1, -2, 2, 1. And a reduced row echelon form, 3, 2, 1. So we get our solution is x equals 3, y equals 2, z equals 1. And so we get the order triple 3, 2, boom. That's it. That's how easy these are. Well, let's look at our next problem. Our coefficient, our augmented matrix is 1. Oops, not 1. Sorry. 3, -3, -3, 3, 2, 3, 1, 2, 3, 2, 0, 0. Okay. Our reduced row echelon form matrix gives us 1, 0, -2/5, or -0.4 if you're using decimals. Then 0, 1, 3/5, or 0.6, 0, and then 0, 0, 0, 1. And you might have been like, cool, my solution is 0, 0, 1. That's absolutely wrong. Okay. Remember, we're not just taking these numbers and saying, this is our solution, we're done. We are creating back our system of equations, right? So we have 1x, 0y, 0z, 0x, 0z, we have 1y, we have no x's, no y's, 1z. And so that is why this gives us a solution. Notice this is in reduced row echelon form. This is not in reduced row echelon form. Even though we told our calculator, hey, put this in reduced row echelon form, why didn't it do it? Well, the reason it didn't put it into reduced row echelon form is because it can't. It is not able to put this into reduced row echelon form because this system of equations cannot be put into reduced row echelon form. Now let's imagine we put this back into a system of equations. Now the first two are pretty simple. We get x minus 2/5 z equals 0, y plus 3/5 z equals 0. But that third equation, 0, 0, 0, 1, we have no x's, no y's, no z's. So I'm going to write this out because I want to make sure we're very clear. So we have 0x plus 0y plus 0z equals 1. What's 0x plus 0y plus 0z? That's 0. All right, so we get 0 equals 1. That's not true. Not true. So this has no solution. We're not a room. I'm just going to move C and kind of put it off to the side. So we say this is no solution. Or our kind of fancy matrices system of equation is we say this is an inconsistent system. Okay. So we could say this. So we could say this. Or we could say it's an inconsistent system. Either of those two statements work. Okay, no solution, inconsistent system. Okay, part C. Again, augmented matrix. Okay. Get negative 1, 1, 1, negative 1, negative 1, 1, 1, negative 1, negative 1, 4, negative 17, negative 22, 7, negative 6, negative 13, 0. Now I wrote these a little close, just kind of a little poor planning on my part, if you will. But you can still kind of see what they are, right? We understand that this is not, this final row isn't 7 minus 6 minus 13 and then a 0. We understand these are different entries. So make sure you're kind of, leaving yourself space to write these out if you have sloppy handwriting or you're worried about it being misinterpreted in which way. Now, use your calculator, put this into reduced row echelon form, and we get 1, 0, negative 7, negative 6. 0, negative 7, negative 6. 0, 1, negative 6, negative 7, and then 0, 0, 0, 0. Again, thinking back to kind of what we did on that last one, we don't have reduced echelon form. So our solution here is not negative 6, negative 7, 0. Again, the reason why it doesn't put it into reduced echelon form is because this matrix cannot be put into reduced echelon form. So what we do here is we use the same idea. We're going to kind of think about putting this back into a system of equations. The first two equations, x minus 7z equals negative 6, y minus 6z equals negative 7. Those are pretty straightforward. It's that last row. Okay, notice we again have 0, 0, 0, which we know from our last example, our last part B, gave us 0x plus 0y plus 0z, which is just 0. This gives me an equation of 0 equals 0. Well, that's true. So when we got a false statement, a not true, that was no solution, okay, or inconsistent system. Here, we have a true statement. That means there are actually infinitely many solutions. Okay, so that's one possibility of things to say, or we could say this is a dependent system. So what that means is that this has infinitely many solutions. What those look like, we can do some more work in future classes and kind of get a better idea of what that looks like, but it doesn't actually work. Now, let's think about what's going on here in a two-dimensional state. 3 dimensions is kind of weird to think about, and I can't draw it 3 dimensions. But in 2 dimensions, if you will, so an inconsistent system. So no solution. What that essentially is two-dimensionally is parallel lines. Okay, there is no intersection. A dependent system minus my terrible drawing skill, is the same line. Okay, so here, parallel. So there's, whoa, sorry about that. Parallel, no solution. Same line, infinite solutions. Okay, so that's what's happening here, kind of two-dimensionally. Three-dimensionally, it's kind of an equivalent. And what's cool is we can actually do systems equations using 15 unknowns, as long as we have enough equations. We have to have as many equations as unknowns to be able to solve it. Okay, so if we had 15 equations and 15 unknowns, we could create a system of equations, put it into reduced echelon form using our calculator, and potentially solve that system. That's pretty cool. Okay. So that's what happens if you get these wonky things. So if we have a false statement, which in our calculator will always result in a 0, 0, 0, 1, or in other words, a 0 equals 1 final equation. If we have a true system or a dependent system, okay, that final row will be a true statement, 0, 0, 0 equals 0, and that will be kind of how those work. If it's anything else, if it is something like this example A, then that means it has a unique singular solution, and that's it. Okay. Now, one thing with this is this only worked with what are called kind of linear systems. And what that means is essentially all of the variables are raised to the first power. If any of these were, say, x squared or y to the fifth or z to the 1/3, this process, this solution process, no longer works. Okay. It has to be in a linear kind of variable terms. All right. Now, because you're able to use your calculator to do this, it really gets pretty simple to solve the system of equations. But the hard part is finding the actual system itself. Going from a word problem into a set of equations is not an easy task for many people. And that's why we're going to do 2 examples on this, and then that'll be the end of this video. So, example 10 here, this first example of the word problem. A diabetic patient wishes to prepare a meal consisting of roasted chicken, mashed potatoes, and peas. A serving of roasted chicken contains 140 calories, 27 grams of protein, and 64 milligrams of sodium. A 1 cup serving of mashed potatoes contains 160 calories, 4 grams of protein, and 636 milligrams of sodium. And a 1 cup serving of peas contains 125 calories, 8 grams of protein, and 139 milligrams of sodium. How many servings of each should be used if the meal is to contain 415 calories, 50.5 grams of protein, and 553 milligrams of sodium? So the first thing we have to do is figure out what in the world are our variables. Well, our variables, okay, let's just be nice to ourselves, say our x, y, and z. So x can be the number of servings of chicken, We'll let y equal the number of servings of mashed potatoes. Number of servings of mashed potatoes. And z, if you haven't guessed, is the number of servings of peas. Okay. So now we have to think about what we know and what we need. Okay. We know the calories, protein, and milligrams of sodium for all 3 of these things. And what we need is we need a meal that has an exact calorie, protein, and sodium amount. So what we're going to do is we're going to create 3 equations that calculate the number of calories in the meal, the amount of protein in the meal, and the amount of sodium in the meal. And so since I need the meal to have 415 calories, okay, that's going to be our first equation. So there's 140 calories in the chicken. So we are going to have 140 times X. So for every one serving of chicken, we have 140 calories. There are 160 calories in the potatoes. So we're going to add 160 times Y. And there's 125 calories in a serving of peas. So we're going to add 125 Z. Remember, we needed to have a total of 415 calories. Now, doing an exactly similar process for the grams of protein, chicken has 27 grams of protein. So we're going to have 27 times X. Potatoes have 4 grams of protein, so plus 4Y. And peas have 8 grams of protein, so plus 8Z. And that needs to equal 50.5. And our last equation is the milligrams of sodium. So chicken has 64 milligrams, so we get 64X. Potatoes have 636 milligrams, so we have plus 636Y. And then peas have 139 milligrams, so plus 139Z. And we want our meal to have 553. 553. So there's our system of equations. Okay. Now, I'm going to tell you right now, on the final, I'm going to ask you to identify the system of equations, write the augmented matrix, write the reduced row echelon form of the matrix, and then give me a solution. Okay. So here we have our system of equations. Our augmented matrix is going to be 140, 160, 125, 415, 27, 4, 8, 50.5, 64, 636, 139, and 553. Now, using your calculator, you can create the matrix in there, put it into reduced row echelon form, and the resulting reduced row echelon form matrix gives us this. Which that means we are going to have 1.5 servings of chicken, a half serving of mashed potatoes, and 1 serving of peas. Okay. So notice we kind of looked at what we had, what information we were given, what we were shooting for, what our goal was. We kind of used it that way. So let's look here. Example 11. Jamal earns a year-end bonus of $5,000 and puts it in 3 one-year investments that pay $243 in simple interest. Part is invested at 3%, part at 4%, and part at 6%. There are $1,500 more invested at 6% than at 3%. Find the amount invested at each rate. So, what do we need to know? What do we know? And what are we looking for, right? So, we need to know the amount invested at each rate. So, we know the amounts invested are at 3%, 4%, and 6%. Okay. What we know is we know the total was given. We know how much interest was accrued. And we know this last thing is there's this relationship between the invested at 6% and the invested at 3%. So we need to use that to create our equations. Okay. But before we even do that, we need to first figure out our variables. Okay. So let X be the amount at 3%, Y amount at 4%, and Z is the amount at 6%. Okay. Now, here's what's cool is we can really easily create our first equation. Because what we know is we know he had $5,000 total that he invested. And if X, Y, and Z are the amounts he invested, then we know that X plus Y plus Z has to equal 5,000. We also know that he gained in 1 year $243 in interest. Okay, since it's simple interest, we don't have to worry about any periodic or compound or any of those things. It's just basic multiply the percent by the amount invested, and that's how much you gained. So if I find the amount invested, or if I take the amount invested, multiply by its interest rate, that will tell me how much interest it gained. So that gives me 0.03x, or 3% of the amount invested in at the 3%, plus 0.04y plus 0.06z. And that has to equal 243. So far, this has been pretty easy, right? And what's cool is this exact process that we're talking right here could be applied to any sort of value type problem. Say like I bought cookies, sandwiches, and drinks. I bought a total of 5,000 things. The cost of them was $243, where, sodas cost 3 cents, sandwiches cost 4 cents, and cookies cost 6 cents, right? I mean, obviously those numbers should be a little different, but that's really what we have here. We have a simple value problem. We have the total amount of things is the first equation. The worth, the value of those things is the second equation. And now, because remember, we need to have as many equations as we have unknowns to be able to solve the problem, we need one more equation. But luckily, we are given one more piece of information. Unfortunately, that piece of information is not as simple and direct to input into an equation. So what I know, and this is something that we really have to kind of take our time with to really make sure we get this correct, there is $15,000 more invested at 6% than at 3%. So the way I like to do these kind of things, when I'm given information like this, if it's something that's at all a challenge for you, I like to really simplify my process, simplify my steps. So I'm going to do this kind of as some side scratch work, okay? And before I write my third equation as in its final form. So the things I'm relating here is the amount invested at 6% and the amount invested at 3%. So in this case, X and Z. So I'm going to write X, and then I'm going to leave a space, then I'm going to leave a space, and Z. And so what these spaces are for is I have plenty of room over here to multiply by something. I left a space to add something or subtract. I left a space here to multiply by something and have space over here to add or subtract. Okay. So what I need to figure out is what do I need to do to what side to make these equal? So I know in this problem, there is 1,500 more invested at 6%. So that means the account with 6% has 1,500 more in it. So how do I make these equal? Okay. Our gut, just our quick, I read this, there's 1,500 more at 6%. So our gut would say, cool, do this. That's what our gut says, but that's wrong. And the reason that's wrong is think of it like a scale. Okay. Is X or Z bigger? Right? Not the percents, but the amount, remember? Right? Based on what information we were given right here, there is 1,500 more invested at 6%. So that means the amount invested at 6% is bigger, right? So I wish you could see my hands right now because I use my hands a lot for this piece. But if you think of it like stacks, the stack of Z is much taller. It's taller by 1500. So how do I make these two stacks even? Do I add to the taller stack? Right, that doesn't make sense. I either need to add to the shorter stack or subtract from the taller stack. So to make these two things equal, I'm going to add 1500 to x. And that gives me a true equation, a balanced equation. Okay? Because z on its own has 1500 more than x does. So to make these two things the same, I need to add 1500 to x. Okay? I hope that makes sense. If it doesn't make sense, go back and rewatch it. See if you can slowly piece it together. And if you need to, message me and we will try and get this nice and crystal clear. Now, the problem here is this equation is not yet ready to go into a matrix. And the reason why is because notice all of the equations we've used so far have had all our variables on one side and all of our constants on the other. And we've had our kind of coefficients and then a result. This is not in that setup yet. I have to manipulate this using our basic algebra skills so that I have all the variables on one side and our constants on the other. And that's really easy. I'm just going to subtract x from both sides. And when I do, I'm going to get negative x plus z equals 1500. Okay. The reason I put it in that order is to kind of match the other equations I've already created. Right? Normally, we would say something like 1500 equals z minus x, which makes sense, right? If I take the amount invested at 6% and I subtract the amount invested at 3%, that's 1500, right? Because there's 1500 more invested at 6%. So I manipulated this, moved it around so that way we have it something that fits into our matrix the way we want it. So we have negative x plus z equals 1500. Again, I'm writing that with that space in there to kind of account for that y. So again, I want you to create your augmented matrix. So 1, 1, 1, 5000, 0.03, 0.04, 0.06, 243, negative 1, 0, 1, 1500. Okay, so that's just our augmented matrix from this system of equations. From there, we can put this into reduced row echelon form. So this is something I do that just helps to kind of symbolize and signify what you're doing. So arrow, so saying I'm taking this augmented matrix into this other matrix by doing reduced row echelon form, or RREF. What I end up with is 1, 0, 0, 0, 1, 0, 0, 0, 1. Right, so that's our reduced row echelon form piece, but we have that final column and we get 1300, 900, 2800. And so what this tells me is that $1,300 invested at 3%, $900 invested at 4%, and lastly, $2,800 invested at 6%. And that's it. Okay, so there were two nice examples of creating the actual system of equations. That first one was just a really nice kind of, all the information is given directly, you just kind of have to plug it in with multiplication. And the second one here was a nice little value problem with a final equation that is some sort of specific case example that you have to then create an equation, build it off of, think about it like that. So with that said, that is the end of this video. I hope you guys learned something, enjoyed this maybe even a little bit, and are able to crush this. If you have not yet gone and watched it, make sure you go and watch the using your calculator to create matrices and put them into reduced row echelon form. All right, you guys, have a great day, and I'll see you at the next video.